I want to talk to you about counting. We all know how to count. You go 1, 2, 3, 4, 5. That's counting by addition. We're always adding 1 to the previous number. And thank you, ancient people, somebody invented 0 and even negative numbers. So we can actually usually start at 0, there's no 0, 1, 2, 3, etc. It's not the only way we can count. We can also count by multiplying by the previous number. And when we do that, we might start with 1, then multiplying by 2, we'd have 2, then 4, then 8, then 16, etc. These two different kinds of series are additive or multiplicative. In mathematics, these are called arithmetic and geometric series. In an arithmetic series, we add to get to the next number, and in a geometric series, we multiply to get to the next number. There's a correspondence between these two forms of counting, which is called exponentiation. So if you take the counting numbers 0, 1, 2, 3, 4, 5, 6, 7, etc., and you think of those as a number of times or a number of 2's that I'm going to multiply together, then when we do the multiplication, we'll end up with the geometric series. So if we have no 2's, what does that mean? Who knows? Anyway, by definition, we get 1. If I have 1 2, then it's just 2. If I have 2 2's and I multiply them together, I get 4. 3 2's, I multiply them together, I get 8. 4 2's, I get 16. 5 2's, 32, etc. So the more 2's I have, the more I multiply. And each time I add 1 2, I get double the previous number. Of course, we can count by adding numbers that are different from 1, and we can count by multiplying by numbers that are different from 2. But for us, this will be sufficient. As a computer scientist, it's useful to memorize some powers of 2, in particular the first 11, going from 2 to the 0th power up to 2 to the 10th. And then after that, it's useful just to remember every 10th power. So starting at 2 to the 10th, we have about 1,000. 2 to the 20th is about 1,000,000. 2 to the 30th is about 1,000,000,000. 2 to the 40th, about 1,000,000,000. 2 to the 50th, a quadrillion. And 2 to the 60th, a quintillion. These numbers will become particularly important in your systems class, where you will look at the representation of numbers in memory. And you'll see that for 32-bit computers, 2 to the 32nd is an important number. For 64-bit computers, 2 to the 64th is an important number. In English, we use the words I've written here, 1,000, 1,000,000, 1,000,000,000. But when we're using these as descriptions of quantities, they're often used in this other form. So I'll say I have a kilobyte or a megabyte or a gigabyte or a terabyte or a petabyte or an exabyte. So when I'm talking about how much memory I have on my machine. And roughly these correspond to exactly what I've written here. Exponentiation is really easy to understand. In order to take a number to its exponent, you simply duplicate the number that many times and then multiply them all together. The reverse operation is also really simple, but it sometimes is more problematic for beginners. It's the logarithm. And if we simply take this table that I've written down and reverse the two sides, so I'll take 1 to 10 to 24, put it on the left, and now the numbers 0 to 10, we'll put them on the right. And note that what I'm doing here is simply the inverse of the exponential. That's called the logarithm. So what is a logarithm? Well, if you have a number in here and I want the log base 2, it's the number of 2's I need to multiply together to get that number. So to get 1024, how many 2's do I have to multiply together? 10. What about to get a quintillion? Well, about 60. Logarithms are no more complicated than exponentials. In fact, if I say that n is 2 to the k, that's identical to saying that log of n is k. In other words, the number I get by multiplying 2 by itself k times is the same thing I get if I take the number and try to figure out how many times I multiply 2 together to get it. They're computing exactly the same thing. Log and exponential are inverses in a formal sense as well. So if you take the log of 2 to the k, then you just get k. And if you take 2 to the log n power, well, you just get n back. We're not going to be doing a huge amount of math with logarithms, but two rules are useful to know. One is that the exponent of 2 to the k plus j is nothing but the exponent of 2 to the k times the exponent of 2 to the j. Similarly, the log of n times m is nothing but the log of n plus the log of m. These kind of laws can be very abstract looking when you see them this way. Let's look at a specific example. Since the exponential distributes in this form, well, let's think about 2 to the 32. 2 to the 32 is nothing but 2 to the second times 2 to the 30th, because 32 is simply 2 plus 30. Well, how can I use that? Well, what's 2 to the second? Looking back on our table, it's just 4. What's 2 to the 30th? That's about 1 billion. And so what is this? It's 4 times 1 billion, or 4 billion. And actually, because we're dealing with 10 to the 24 instead of 1,000, there's a little bit of error here. It's a little bit more than 4 billion. But for most purposes, 4 billion, fine. What about 2 to the 64th? Well, 64 is nothing but 4 plus 60. So that's 2 to the 4th times 2 to the 60th. 2 to the 4th is 16. 2 to the 60th is a quintillion. So we're at about 16 quintillion. And you can see here that the error sort of piles up a bit. It's actually closer to 18 quintillion, but 16 quintillion's good enough. Quintillion's a lot. That's a big number, so we're fine. 16 quintillion. We can also apply these laws for logarithms. So if we have the log of 4 billion, we might wonder, what is that? Well, since 4 billion is nothing but 4 times 1 billion, we can simply take the log of 4 plus the log of 1 billion, and that will give us the log of 4 billion. So log of 4 is just 2, log of 1 billion, 30, and therefore the log of 4 billion is 32. What about the log of 16 quintillion? Same thing applies. We take the log of 16, the log of quintillion, and that's 4 plus 60, or 64. Just like the number 10 is particularly important to us in our daily lives, the number 2 is particularly important in computer science. But in fact, we can do exponentials or logarithms with any base. And when we have a general logarithm, we write a subscript b for the base. And there's a way to relate logarithms with different bases. The details of the formula aren't that important to us, but what is important is that logs at different bases are related by a constant. And let me just show you by example. Suppose we have log base 2, which I can write simply as LG, so the log base 2 of n, and I want to know how that relates to the log base 1000, more or less. And you can see by this formula, what I'm going to do is take the log base 2 and divide it by the log base 2 of 1024. So since the log base 2 of 1024 is 10, I just divide by 10. So the log of 1,000 is not that different from the log of 2. They're related by a factor of 10. Another really common logarithm is in fact the log base 10. And it's interesting to see what the relationship is between these two. And it's about a factor of 3. When you get more precise, the log base 2 of 10 is actually 3.32 blah, 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 blah. So again, the exact details of this equation aren't important to us. I don't expect you to memorize this equation, but it's important to know that any two logarithms are going to be related simply by a constant factor. If you'd like a more artistic introduction to the subject of logarithms, you should watch this video. It's fun.